now let us see that what is the pressure inside the liquid drop. So, we here neglect gravity. So, you see that is first method we will use three different method. First method will be excess pressure formula. So, we will directly use our excess pressure formula derived to determine the pressure inside a liquid drop. So, we have our liquid drop like this, it is liquid inside it and it has a radius small r. So, this has a small radius r. Now let us take a point 1 and 2. So, consider 2 points 1 and 2, where 1 is inside the liquid drop and 2 outside. So, now according to excess pressure formula, P1 will be more than P2. So, we have P1 minus P2 is equal to 2S by R. So, we have excess pressure formula H for spherical surface. This is 2S by R, P is equal to 2S by R. Now, here P1 is P inside or internal minus P naught or PA, the atmospheric pressure. So, inside pressure is equal to atmospheric pressure plus 2S by R. So, thus the excess pressure formula directly tells us how to what is the pressure inside the liquid drop. Now, second method. So, equilibrium of force. So, this method is called equilibrium of force method. So, what we do? So, you see here, this is my liquid drop and I mentally divide the drop into 2 pieces, and now you analyze the only one drop, semi drop. So, you see here, this drop is pulled by the lower drop from the surface by a surface tension force. The liquid drop has only one skin. So, consider the equilibrium of a semi drop. So, now you see here there are some forces, external forces. I say that external atmospheric pressure is P naught, and so the total force is the cross section, that is pi r square. Now, from inside also the liquid will exert a pressure force here from all directions, and the resultant along the outward is P inside by pi r square, and the total length is here 2 pi r. So, 2 pi r into S is the surface tension force. So, now here P this is outer pressure, atmospheric pressure, P naught I say, P naught into pi r square plus S into 2 pi r is equal to P pi r square, implies, let us divide by pi r square. So, P is P naught plus 2S by R. Thus, we see again by this equilibrium of force method that the pressure inside the liquid is equal to 2S by R more than the atmospheric pressure. Now, the third method, what is the third method? This is virtual energy method. So, what is this method? So, if we have a liquid drop and it has a radius r and the system is in equilibrium, that means the liquid drop is in equilibrium. If its radius rises to small dr, by small dr radius, that means the total radius is r plus dr, then the work done by the unbalanced force is equal to the surface energy, that is the change in the free energy of the system. So, let R be the equilibrium radius of a liquid drop. So, let R be the radius. Now, let the radius increases by dr virtually. So, now you see what is area previously 4 pi r square. Now, the area will change to 4 pi r dr, 2 will be there. So, it will become 8 pi r dr. So, this is the area. Now, there will be a change in volume also. V is equal to 4 by 3 pi r cube, implies the change in volume is 4 by 3 pi 3 r square dr. So, 3 cancel. So, we have dV is equal to 4 pi r square dr. This is dV also. Now, we know that the surface tension is equal to the work done or the free energy per unit area of the film. That means whatever work we have done, that will be S into dA. And how much work? The hydrostatic work done by the excess pressure is P into change in volume is S into change in area. This implies excess pressure into dV, that is the work done by the excess pressure, is equal to the surface tension S into area. So, P is P, and you can see dV as 4 pi r square dr, and this is equal to S into dA. dA from here we see it is 8 pi r dr. So, dr cancel, pi cancel. So, P is equal to excess pressure is equal to this 4 cancel. So, 2 S by R. Now, excess pressure is outside pressure is P naught. So, P minus P naught is excess pressure, P is equal to 2S by R. So, P inside is P naught plus 2S by R. So, thus we have seen by 3 different techniques we have arrived at the same result, that the pressure inside a liquid drop is more than the outside pressure by 2S by R. Now, let us see the pressure inside a liquid inside a bubble.